For our final set of examples, we're going to take a look at something that doesn't use one of the formulas provided, but it is an exponential model, but the model is being provided to us in the context of the problem. So here we go. Problem number 7. When a person takes a dosage of I milligrams of ibuprofen, so I represents the milligrams of ibuprofen that you take in a dose, okay? The amount A in milligrams of medication remaining in the bloodstream after T hours can be modeled by this equation. So we're going to use this provided function right here. Okay, so A is the amount of ibuprofen that remains in your bloodstream after a period of time. T is time measured in hours. And then I is what was the initial dose that you took of ibuprofen. Okay, so part A, determine the amount of ibuprofen remaining in, sorry, there's a typo here, in Carla's bloodstream if she took 400 milligrams, 5 hours ago. So 400 milligrams. Okay, so A equals P, nope, sorry, I'm so used to A and P. I equals, and then T equals. All right, so what do we know? We know that Carla took 400 milligrams. So that's the amount that she took, and she took it 5 hours ago. So what's left in her bloodstream? So this is going to be an evaluate problem where we're just plugging in, okay, I is 400, and then we've got 0.71, and then to the T power. And then I type that into a calculator to see what I end up with. All right, so 400 times 0.71 to the 5th power comes out to 72.169 milligrams. All right, so approximately 72 milligrams remain at this point in time. Okay, so that's what I'm going to write. Approximately 72 milligrams remain after 5 hours, okay? And these models, these functions that we're taking a look at here, these are developed by doing scientific studies and then measuring how much of a drug is left in someone's bloodstream after a period of time. And they use these models to try to figure out appropriate dosing for various ages, health conditions, all sorts of stuff like that. And that's why when you look on a medication bottle, it tells you to take so much every 4 to 6 hours or whatever the time frame is, and there's wiggle room there, but they're using it to make sure that there's an appropriate dose remaining in your bloodstream after a period of time, all right, and to make sure you're not getting too much in your bloodstream, all right? So that's part A. Part B, Paul took 325 milligrams of ibuprofen, and he now has 98 milligrams left in his bloodstream. How long ago did he take the medication? Now, why would we ever need to work it this way? Well, what if Paul ends up going to the doctor's office and he's getting tested for something, or knows he took the meds but forgot when he took it? Well, they could figure out, based off of this information, if they've done blood work, how long ago he took that medication, right? So we have the ending amount, the initial amount, and the amount of time. And it says he took 325 milligrams, and there's 98 milligrams remaining. So what's left? How long ago did it happen, rather? Sorry. So I'm going to plug in that 98 takes the place of A, 325 takes the place of I. We've got the base of 0.71 that was provided to the T power. And now we're back to an exponential equation to solve. So we're going to divide out the 325. Now 98 over 325 is not a pretty decimal, so I'm going to leave it as a fraction, 98 over 325. And that's equal to 0.71 to the T power. And now I'm going to take the log of both sides. You could do common log or natural log. I'm going to go with common log here. So now I have the log of 98 over 325 is equal to, and I can pull the T out in front, log of 0.71. So from here, I can say that T is equal to the log on the left with the fraction divided by the log on the right, 0.71. And the parentheses you see here are the only parentheses you need on your calculator. Now when I do this, I get T equals 3.5001, I think it is. So this is approximately 3.5, and we can safely round it to 3.5 knowing that it was followed by a 001, okay? So for my final answer, I can write that Paul took the medicine (3.5 hours ago. Or I could say, you know, you can phrase the sentences in different ways. Your sentences do not need to be identical to mine. They just need to clearly communicate what your final answer is. So you could say, Paul took 325 milligrams of ibuprofen 3.5 hours ago. We can get as specific as we want, okay? All right. Now this final problem is a little bit different. I think you'll see why as we start reading through it. All right. Radioisotopes of different elements have different half-lives. And if you've done this in like a science or a chemistry class, you're familiar with this concept already. But, okay, here we go. Magnesium-27 has a half-life of 9.45 minutes. What that means is every 9.45 minutes, there's exactly half the amount that there was 9.45 minutes prior, okay? So if I started with, say, 20 grams, after 9.45 minutes, I'm down to only 10 grams remaining, and then another 9.45 minutes after that, I'm down to only 5, and so on and so on, okay? What is the decay constant? Okay, key phrase there, decay constant. For magnesium-27, round to 5 decimal places, all right? We're also being told how to round our final answer, so we need to pay attention to that. So 5 decimals in our final answer. All right, well, what model makes sense? Well, there's no interest being talked about, so it can't be formula 1 or 2. There's no value of an object. There's no money involved here, so it can't be equation 4. So I have to go with equation 3, which is y equals NE to the KT. And that's also the only one that has the decay constant, the growth or decay constant is the K value. All right, so we've got y equals N equals K equals T equals. All right, now we're given an amount of time, 9.45 minutes. And we were told to find the decay constant, which is K. But that's all we were given, which means we have too many unknowns. But that doesn't mean we can't solve the problem here. We're going to pick our own numbers for this, but there's a special relationship. Let's say there are, 100 grams to start with, okay? Grams, milligrams, whatever amount we're talking about. Let's say we start with 100. Well, after 9.45 minutes, how much is left? Well, that's the half-life, so that means we're down to 50 grams, okay? So I can use any numbers here as long as y is half of n. Now that is specific to half-life problems, okay? That's the only time that we would have to come up with our own numbers. Everything else that you've seen, yeah, we're provided all the information that we need, okay? So this is that jump that we're gonna have to make, but specifically on the radioisotope problems only with half-lives. All right, so now I'm gonna have, not 100. The ending amount is 50. The starting amount is 100, and then I have e to the k, t is 9.45. All right, so now we wanna solve this equation, so we wanna divide out the 100, divide out the 100. We want to isolate the exponential, so now we have 1/2. You can do 0.5 here if you prefer. E to the 9.45k. All right. And now because it's a E problem, I'm going to take the natural log of both sides to cancel off the E. And that's going to leave me with the natural log of 1/2 is equal to 9.45k. So k would have to equal the natural log of 1/2 divided by 9.45. So that's going to give me k is equal to the natural log of 1/2 divided by 9.45. And it's set to go to 5 decimal places, so negative 0.0733, and then I've got a 4, 8 becomes a 5. All right. Now, it makes sense for it to be negative here because we're talking about something decaying, but E is a numerical base that's approximately 2.718. So that would indicate a growth model, so I'd have to have a negative exponent to actually make it decay. Don't worry about that. Just know that it's okay to get a negative whenever you're talking about growth and decay. Decay values should come out with negative rates, and growth values will have positive rates. All right, sentence for a final answer, I can say the decay constant for, and we can get specific here, magnesium 27 is negative 0.07335. Now there's no unit there because it's just a constant, okay? So that's my final answer. All right. So what you want to be focusing on is, how do I know which formula to use when? How do I identify what numbers go where? And then solving the equation from there. Again, if we're solving for an exponent, logarithms are going to get involved. And if the variable is not in the exponent, then we can solve using other techniques that we're more familiar with. All right? If you have any questions, please reach out and let me know. Otherwise, good luck with your homework. See you soon.